So let's look at the PageRank algorithm in a bit more mathematical detail. So the PageRank algorithm is an iterative algorithm, meaning that we update the scores at every step, and we do this according to this update rule. The scores are stored as a vector R, which we call the rank vector. And we'll stop updating the algorithm, or we'll stop the algorithm when we see that subsequent iterations do not change the value of R. That is, R at the next step is approximately equal to R at the previous step. Once the scores have converged to a final value, we can then rank our pages accordingly, with the page with the highest score being the highest ranked page, and so on. The update rule has two terms. So the first term updates the scores based on the connectivity in the network. And the second term is a constant term where n is the number of pages on the internet, or more generally, the number of nodes in the network. And d is a parameter which we can choose. This term becomes important when we have situations where we have pages in our networks that have no incoming links, that is, no other pages linked to that page. And this term ensures that no page will have a 0 score. For our small network, it turns out we have no pages that have no incoming links, so we can choose to set the parameter d to 1, which gives us this simplified update rule. The last ingredient left to discuss is the matrix M. The matrix M captures the connectivity between all the nodes in our network, and it's constructed as follows. So first check if a page J links to a page R. For example, does South Africa link to Nigeria's page? If this is not the case, then set the element Mij to 0. If this is the case, then you set the element Mij to a factor 1 over Lj out, where Lj out is the total number of outgoing links from page J. As an optional step, we can also renormalize or rescale the R vector. And this is very convenient as it keeps the total score constant throughout the iterations. In the simulations I'll show you in the next slides, I have normalized the vector so that the total score is always 100. This step is allowed because multiplying all the scores by the same factor will not change their relative ranks. Now that we've covered the mathematics, let's simulate the PageRank algorithm for our tiny network. So I've started off at step 0 by setting all the scores to the same value, that's 14. But this is an arbitrary choice, so feel free to experiment with different initial conditions and see how that changes the final result. So if we make one update, we'll see that the changes are somewhat significant. Some page scores have gone up while some have gone down. If we do another iteration, you'll see that there's also been some changes, but they're a bit less. Let's do a few more updates. So on the third step, these are the scores, the fourth, the fifth, and you can see the results are starting to stabilize. And by the time we've reached the sixth, seventh, and eighth iterations, you can see the scores have stabilized to their final values. And now we can rank the pages according to these final scores. So these are our final rankings. You can see Nigeria has been ranked the highest, while Kenya and Uganda are tied for the lowest rank. Was this in line with your initial guess? If not, you can go back to the original network and see if this ranking, see if you can convince yourself that this ranking makes sense given the network. It turns out that for our simplified version of the PageRank algorithm, we could have actually predicted these rankings beforehand. And you'll see in the next video how that can be done.